Let's introduce the concept of derivatives and gradients. On the left, you can see a curve that is drawn in a Cartesian plane. A curve is also called a function. On the right, we see the Cartesian plane defined by the x-axis, which is the horizontal one, and the y-axis, which is the vertical one, and the two axes meet in the origin of the plane, the point 0. Here the Cartesian plane is divided in 4 regions that are called quadrants. In the first one, we find all the points that have both the x and the y positive. In the second quadrant, there are points that have negative x values but positive y values. In the third quadrant, there are points that have both the x and the y values negative. And finally, in the fourth quadrant, there are points that have negative y but positive x. Now, let's start by reproducing the curve in our Cartesian plane. Let's define 2 points on the x-axis, and we call these 2 points x1 and x2. In this case, we have that x2 is larger than x1. Now we find the corresponding value of x1, so we draw first a vertical line starting from x1 that goes till it touches the curve, and then from that point on the curve we draw a horizontal line that till we find the y-axis. The value of y in that point is y1. We do the same with x2 to find y2. Then we ask ourselves, is y2 larger than y1 or is it smaller? Well, in this case, we have that y2 is larger than y1. And in this case, we can say that between x1 and x2, the curve or the function is increasing, which means that it has a positive gradient. As the gradient is often indicated with the letter m, we can write in this region that m is larger than 0. Now let's consider other 2 points on the x-axis, but in a different location this time. So x1 and x2, and in this case again x2 is larger than x1. We find the correspondent y1 and y2 values, and we ask ourselves which one is the largest, and in this case we can say that y2 is smaller than y1. So we are in a different case than the one we saw before, and we can say that between x1 and x2 the curve or the function is decreasing, which means that it has a negative gradient m smaller than 0. If we repeat this game for different points on the x-axis, we find in general that the green parts are the ones where the function is increasing, so they have a positive gradient m larger than 0, while the red parts are the ones where the function is decreasing, so the curve has a negative gradient m smaller than 0. Intuitively, you can see that the function is increasing when the curve is going towards larger y values, while it is decreasing when the curve is going towards lower y values. Now, let's consider a point on the curve where we know that the curve is increasing, so m is larger than 0, the gradient. Now we can imagine to draw a line that touches the curve only in that particular point. This line that here is in yellow is called tangent. If we change the location of the point, then we can see how the line also changes, in particular its inclination changes. And these lines that are the tangents are the straight lines that touch the curve only in one point. Now, let's consider another point in a location, in a region where the curve is decreasing. If we draw the tangent to the curve in this point, we can see how the inclination is completely different with respect to the previous case. And again, if we change the location and we go to another point where the curve is decreasing, the inclination of the tangent again changes. Now let's consider a point that is located exactly where the curve changes from being increasing to being decreasing. The tangent to the curve in this point is a horizontal line and the gradient is m equals 0. This is true for all the points where the curve changes from being decreasing to being increasing. For example, this point. So the gradient is 0 in all the points where a function changes from increasing to decreasing and vice versa. But the gradient is also 0, for example, in this point, where the curve is almost flat and parallel to the x-axis. So in general, all the points of a curve where the tangent is a line that is parallel to the x-axis have a gradient equals to 0. Now, let's calculate the average gradient m in an interval of x values. So again, we define two values of x and the corresponding y values. There is a formula to compute the average gradient between x1 and x2, and the formula is this one. So the gradient is the difference between y2 and y1 divided by the difference between x2 minus x1. So this formula gives us the average gradient between x2 and x1. Now, if we draw the line that connects the 2 points x1 and x2 on the curve, then we can see that the average gradient of the curve between 2 points is telling us something about the inclination of the line that passes through the 2 points. Now, let's calculate the gradient not in an interval of x values, but in one point. For example, the point C, and I also drawn the yellow line that is the tangent to the curve in the point C. Now the gradient of the curve at the point C is the gradient of the tangent to the curve at C. This is definition. But what we have is that we cannot use the formula that we saw before. Why? Because this time x1 minus x2 minus x1 is equal to 0. And also y2 minus y1 is equal to 0. So the formula would be m equal 0 divided by 0. So let's see how we can calculate the gradient in one point of the curve C. We can imagine to consider 2 points, x1 and x2, that are very close to C, so that the gradient in that very small range of x values is very similar to the gradient in C. So let's do this mental experiment of taking values of x1 and x2 that are very close to xc. So in this mental experiment, it is like the intervals are becoming very small. In a way, they are becoming infinitesimally small. And since in mathematics, infinitesimals are indicated with the letter D, then we can write that the gradient m is the ratio between an infinitesimal range of y values and the corresponding infinitesimal range of x values. So given a function f, the operator that we just saw, the y over the x, is its derivative, and it can also be indicated with this symbol, with this apex after the letter f of the function. And when we compute the derivative of a function, we say that we are differentiating the function. And we have to remember that the derivative of a function in one point is the gradient of the function in that point, and is related to the inclination of the tangent to the curve in that particular point. So now we can start looking at some example. Let's consider this function f, which is equal to minus x to the power of 3 plus 3x to the power of 2 plus 9. We can see that this function is made up of the sum of 3 functions that we can call g, and then we have h, and we have a constant k, which is our number 9. Now let's write here all the rules to compute derivatives. Well, the first rule is that the derivative of a function that is the sum of other functions is just the sums of the derivatives of those other functions. So in our case, we just have to compute the derivatives of the function g, h, and k to obtain the derivative of the function f. So let's start with the first term, minus x to the power of 3, which is our function g. We want to compute the derivative of this function, and we have this rule number 2. So when the function is equal to k, a constant, multiplied by x to the power of n, where n is any integer, then its derivative is n plus multiplied by k multiplied by x to the power of n minus 1. So in our case, the derivative of g is minus, which is our k constant. Then we have the number 3, which is n, and then we multiply everything for x to the power of n, which in our case is 3, minus 1. So the derivative becomes minus 3x to the power of 2. Now let's go to the second term, the function h, which is 3 multiplied by x to the power of 2. We can apply the second rule that is in our box of rules, and we find that the derivative of h is plus 3 multiplied by 2, which is our n, multiplied by x to the power of n minus 1, so 2 minus 1. So the derivative is, in this case, is 6, which is the result of 3 multiplied by 2, x to the power of 1. And since x to the power of 1 is x, the final derivative is 6x. Then we have the third element of our function, which is a constant 9. And we also have another rule, which is that the derivative of a constant is always equal to 0. So now we apply the first rule that we wrote in our box of rules, and we write that the derivative of f is the sum of the derivatives of the functions g, h, and k. And so the derivative of f is equal to minus 3x to the power of 2 plus 6x plus 0. We can ignore the plus 0, and so this is the final derivative of the function f. Now let's see another example. This time we have the function g, which is defined as 2 multiplied per x to the power of 4 minus x plus 9. So first thing we have to do, we have to remove the parentheses, and so the function g becomes 2x to the power of 4 minus 2x plus 9. And then we are again in the same case as before, so our function g is the sum of 3 different functions, the function f, the function h, and the constant k, which is 9 in this case. So we have to compute the derivatives of the individual functions. So let's start with the derivative of the first function f, which is 2x to the power of 4. So its derivative is plus 2, which is our k, if we look at the second rule. And then we have n, which is 4, multiplied by x per to the power of n minus 1, so 4 minus 1. And so the derivative of the function f is plus 8x to the power of 3. Now let's go to the second function, the function h, which is minus 2x. So this time its derivative is again minus 2 multiplied by 1, which is the n of the second rule, multiplied by x to the power of n minus 1, so 1 minus 1. So this becomes becomes minus 2x to the power of 0, and since x to the power of 0 is 1, then the derivative of h becomes just minus 2. Now we have the third function that is a constant, and we know that the derivative of a constant is equal to 0, and so the derivative of the function g becomes plus 8x to the power of 3 minus 2 plus 0. So we ignore the plus 0, and the final derivative of the function g is plus 8x to the power of 3 minus 2. Now we can look at another example where we have to compute the derivative of the function that is between parentheses. So the first thing that we have to do is to compute the multiplications between the members that are inside the parentheses. And so we can write that we have to compute the derivative of x multiplied by the term 2x multiplied by 3x is 6x squared. And then we have the multiplication between 2x and 5, which is plus 10x. The next one is the multiplication between minus 1 and 3x, which is minus 3x. And finally, the multiplication between minus 1 and 5, which is minus 5. But we still have a parenthesis inside the squared brackets. And so we now remove this parenthesis. We compute first the sum between 10x minus 3x inside the parentheses, which is 7x. And then in the next step, we compute the multiplication with the x that was outside the parentheses. And so at the end, we have to compute the derivative of the function 6x to the power of 3 plus 7x to the power of 2 minus 5x. And this derivative is this one, so we have 6, which is the k of the first term, multiplied by 3, which is the n of the first term, multiplied by x to the power of n minus 1, which is 3 minus 1. Then we have the second term, so plus 7, which is the k of the second term, multiplied by 2, which is the n of the second term, multiplied by x to the power of n minus 1, so 2 minus 1. And then we have the last term, and so minus 5 multiplied by 1, which is the n of the last term, multiplied by x to the power of 1 minus 1. This expression then becomes 18x to the power of 2 plus 14x minus 5x to the power of 0, which is 18x to the power of 2 plus 14x minus 5, and this is the final answer, the final derivative of the initial function. We have another example where we have to compute the derivative of this function h, which is x to the power of 3 minus 6x to the power of 2 plus 9x plus 16. Again, we apply the first rule, so we have to compute the derivatives of all the functions that form the function h. So the first term, the derivative of x to the power of 3 is 3x to the power of 3 minus 1. Then we have the derivative of the second term, which is minus 6 multiplied by 2 multiplied by x to the power of 2 minus 1. Then we have the derivative of the third term, which is just plus 9. And the derivative of the last term, 16, is a constant, so it's 0. So the derivative of h becomes 3x to the power of 2 minus 12x plus 9, which is the final answer.